In this video, we're going to work through two different conservation of energy problems in physics. So let's go ahead and take a look at this first example right here. It says, a 500 kilogram roller coaster car is released from rest at the top of an 80-meter hill. Find the speed of the car at the bottom of the hill, assuming no friction. So I've sketched out this situation. We have this roller coaster car. It's at the top of an 80-meter hill, and it's currently at rest. We want to know when it is released and it goes down the hill, what will be the speed of that car at the bottom of the hill? So let's say right down here, when it actually is at ground level. So in this type of problem, the only force that is actually acting on this roller coaster car is gravity. And we call gravity a conservative force. So when only conservative forces are acting on an object, what we know is that the initial mechanical energy of the object, let's write ME initial, must be equal to the final mechanical energy. So ME final. Now, one thing we know about mechanical energy is that it's simply the sum of the potential energy and the kinetic energy of an object. So when this car is at rest at the top of this hill, it has potential energy due to its height above the Earth's surface, but it doesn't have any kinetic energy because it's not in motion at all. So we only have potential energy right here. But at the bottom of the hill, once the cart actually reaches the ground, it no longer has any potential energy, but it does have kinetic energy because it's in motion. So what we can say is that this initial potential energy must be equal to this final kinetic energy. So we can say PE, the potential energy, is equal to the kinetic energy. Now, the potential energy of the car, that's calculated as the mass of the car times the magnitude of gravity times the height above the Earth's surface. And the kinetic energy is calculated as 1/2 times mass times velocity squared. So we'll notice there's an m on both sides of the equation, so we can cancel those out. And remember, we're trying to solve for the final velocity at the bottom of this hill. So to solve for v, we can multiply both sides by 2, so we get 2gh is equal to v squared. And to solve for v, we just take the square root of both sides. So we'll get, let's write it on this left-hand side, v is equal to the square root of 2 times the magnitude of gravity times the height. So if we fill in these values, we get the square root of 2 times the magnitude of gravity is 9.8, and that would be meters per second squared. And the height we know is 80 meters, so that will be 80. And when you punch this into a calculator, this comes out to about 39.6. And since we're talking about velocity, our units will be meters per second. So that will be the final speed of this roller coaster car when it actually reaches the bottom of the hill. Okay, now let's take a look at our second example. It says, a 3 kilogram ball rolling along with a speed of 2 meters per second along a flat surface starts up a hill. How high does the ball roll up the hill before it stops? Again, assuming no friction. So I've sketched out this situation. We have this ball that's rolling on a flat surface at 2 meters per second, and then it starts to go up a hill. And our question is, how high up the hill is this ball actually going to go before it comes to a stop? So again, in this scenario, the only force that's acting on this ball is going to be gravity, which will be working against the ball as it actually is trying to go up the hill. So in this scenario, again, because gravity is the only force working on this ball, that's a conservative force. So we know that the mechanical energy, again, the initial mechanical energy of this ball, it must be equal to the final mechanical energy. And in this case, the initial mechanical energy, this ball only has kinetic energy because it's at the ground level, so it has no potential energy, but it is in motion, so it has kinetic energy. So we can say the kinetic energy, the initial kinetic energy, must be equal to, once the ball actually reaches a point up here on the hill where it stops, it no longer has kinetic energy, but it does have potential energy because it has climbed up a certain distance above the Earth's surface. So we'll say it only has potential energy here, and it only has kinetic energy here. So we can say this initial kinetic energy must be equal to this final potential energy. And again, we're just going to fill in the values that we know. So again, kinetic energy, that's 1/2 times mv squared is equal to potential energy, that's mgh. So again, what we'll notice is that the masses cancel out. And in this case, we're trying to solve for h, the height, how high the ball is going to go up the hill. So to solve for h, we just need to divide both sides of this equation by g. So what we end up with is h is equal to, we have v squared over 2 times g. So if we fill in the values that we know, we get v, the velocity is 2, so we get 2 squared, which is 4, over 2 times the magnitude of gravity, which is 9.8. Now we can divide the numerator and denominator both by 2, so this becomes a 2, and this becomes a 1. So really we get 2 divided by 9.8, and that comes out to about 0.2. And we're talking about height, so we'll say meters. So this is how high up the hill that the ball is going to roll before it comes to a stop. So those were 2 examples of how to solve very common conservation of energy problems in physics.